basement. But damaging devices is not just a hobby I've tinkered with over time. It's a complex body of work researched in the field and in the lab. It is constantly tested,
10 minutes on this one, let's see what happens.
meticulously studied,
We got some sparks at 7:30.
and organically evolving with every case. Hello, everyone. Thank you for being here today. My name is Steve Watson with VTO Labs, and you are here for a webinar on fire damage devices. We're so excited that many of you chose to join today. We've got a lot of interesting information to share with you about research of what we've been learning on fire damage devices, and we want to share that with you to get that out to the community so it can be helpful to you. I have Matt Domanic from VTO here with me as well. You'll find him in chat on the right side of the screen. And if you have questions as we're going through between myself and Matt, we should be able to answer them. He'll be in chat so that I can pay attention to you here on the screen. Let me show you what we're going to walk through today. We have a number of topics to cover. I want to share with you how we do research at VTO and the kinds of things that we research, because I think it's helpful to understand how you can be researching topics that you're struggling with in your agency. I have several different really great videos to show you about some of the work we've been doing. I think video helps to tell a great story, so I think you'll really enjoy it. And then we want to give you things that you can walk away with. What are some of the practices we use at VTO Labs on a daily basis to get data out of devices that have been damaged, burned, underwater, devices that everybody else has just kind of written off? That's what we do here often. And we have tips that we want to share with you today that you can put into practice in your own organizations. So if we have a look at the research, we research damage, not just damage, but damage and new technology. And you can see a number of things here on the screen. I started by researching what liquids do to devices. And it started years ago. I had a couple of devices come across my lab bench in the course of a week. And one of them had fallen in a swimming pool, and one of them had gone through a laundry machine. And as I looked at those devices and looked at the circuit boards, they failed for two different reasons. One of them had a short circuit across the board. The other had significant corrosion across the printed circuit board and the contacts that were there. And I was trying to understand why was it different? What was different about these two different devices and the way that they failed in different ways? This has led me down a path of looking how fire damages devices, what happens when impact damages. You saw in the video at the beginning of dropping things from very high altitude onto concrete. Ballistics damage. We've tested every firearm caliber available in the US, from handguns all the way up to long guns. 50 caliber rounds we've put through phones and still had success getting data off of those devices. Chemical damage. What happens when chemicals are exposed to a device, and does that stop you from being able to pull data off? Biohazard contaminated devices, drones. Many of you have heard of our work in drones, and we have lots of efforts underway looking at different kinds of Internet of Things devices. So how do we do research at VTO? I'm not at that slide yet. Let me tell you about the liquid damage a little bit. The liquid damage research that we're doing, we're currently in the middle of a 20-year longevity study where we have devices underwater, under freshwater and saltwater. We have completed year 6 of that study. We have a 100% success rate of pulling the data out of the devices that have been submerged underwater. And if you come into our laboratory at some point, we'll show you the devices sitting in jars in a cabinet that stay there until it's their time to come out of the water. Our next devices will come out in May and June respectively for freshwater and saltwater, and that will be year 7 at that point. In 2018, we did a study on hygroscopic capacity of integrated circuit packages and circuit boards. And hygroscopic capacity is the ability of devices to absorb water. One of our hypotheses when we were looking at the damage that happens on boards is we were seeing that the circuit boards would actually absorb water and then release some of that water out. So we wanted to measure it. If it's happening, can it be measured, and how can we measure it? And we found that yes, circuit boards and chips even absorb water, and that's why drying is so important, so that you can safely get the water out before you turn it on and introduce an electrical current that could cause a short circuit. We looked at multiple different methods for drying the circuit boards and the chips, 7 different methods that we investigated on what's the best way to dry devices. And we've done research on how can you recover data from devices that have been submerged in human blood. We've had agencies call us and say, we've been told that it's impossible to get data out of devices covered in blood. It's not impossible. You just need to know how to address these devices and clean them, and you can still retrieve the data. Fire damage. We have tested so many things about fire. We've tested different temperatures all the way up to 1,500 degrees Celsius, Fahrenheit. We've tested different durations, and that was really introduced to us by the fire investigators that we were working with, because fire in a residential house fire or in a building fire, sometimes the fire is put out quickly. Sometimes the fire may smolder for a long amount of time. So we wanted to see what those variables were on how a different duration of time can affect the ability to get data. Different fuel sources. We have put devices in microwaves to see if it damages it, where you can't get the data out. Car fires, fire suppression foam. That was in the US, there are 3 major types of foam that are used. All of the manufacturers say that it's damaging to the electronics. And what we've learned is that they mean if you put something wet on a device, it's not going to work the same way. The fire suppression foam does not prevent you from getting the data out of the device, though. The data is still there. The data still can be retrieved, even if the fire's been put out with fire suppression foam. We have about 4 years of dealing with devices that have been very heavily damaged by fire, or with the process of extinguishing those devices. Other types of damage, impact damage, you saw an example of that in the early video. Where we have taken devices up high enough that they reach terminal velocity, which is the maximum rate they can fall before they hit the ground. Still had success getting data out of them. Ballistics damage and chemical damage. The chemical damage is interesting because we've looked at both things that start fires, the fire accelerants, but we've also looked at if devices have been in a meth laboratory kind of situation with very volatile and dangerous chemicals. Can those be cleaned in such a way that you can still retrieve the data off the devices? The research principles that we have here at VTO, and the very most important thing to us is it must be applicable to real world problem sets. If we go off and we're figuring out how to do things, and we come to you and you tell us, we're never going to use this. This is not interesting at all. We've all seen research that has come out of organizations or even universities before that said, wow, that's really impressive. I don't know how I'll ever use that. What's important to us is that we do the things that will help you in your daily job, help you when you encounter something that you don't often see. What do I do? Who can I turn to for help? The research, it should have input from those who are experiencing the issues. If we go off as a bunch of techies and figure out how to do this, and those of you that are doing this on a daily basis say that's not how it happens. That's whenever we get a fire damage device, that's not what we do. We need to hear from you. We need to partner with you. And that's why the last part of this is research must be multidisciplinary. Often in digital forensics, we take really smart people who know a lot about devices, and we forget that there's people in other disciplines that know more than we do. Before we started into this, I didn't know anything about fires, how they start, how they get put out. And for me to try to figure that out when there's people that know this world and know this science far better than we do, it would be negligent for us not to take their input and incorporate that into the research that we're doing. Let me show you a video about some recent research we did, and you'll see those principles I just said put into practice because we partnered with a local fire investigator right here in Colorado to burn devices, and so he could help us burn them in a way that he knows what happens when these things burn, how long they're exposed to heat and fire and steam. And let me show you the video. You'll love it.
We are at a fire training academy today with one of the agencies that we frequently partner with. It's about 6 degrees outside, and we are getting ready to burn these wooden structures that you see here. Inside of them, we have placed computers, hard drives, a desktop computer, and we're looking to see what damage occurs to the hard drives in a simulated fire environment so that once we pull these devices out and take them back to the lab, we can replicate what fire investigators are dealing with on a regular basis all over the world.
The only fuel that we are using today is going to be ordinary combustibles. We are only using wood. It will be a clean experiment in that regard. The only caveat on that is that we are going to jumpstart the off-gassing with a propane torch. A fire will be ignited in a fire room on the first floor of the dollhouse. Once the fire has progressed from the incipient, from the growth phase, and a bidirectional vent is established at the opening, which means that there will be smoke exhausting from one side and clean air coming in at the bottom.
What we have here today are a number of devices that contain internal hard drives that store media on the device themselves. Of the different devices that we have are a few laptops. So this one and this one here, they have internal spinning drives, and these other 3 laptops have internal solid-state drives. Some of the other devices we have are a desktop computer with 2 internal hard drives, an Xbox 360 with an internal hard drive, and 2 other loose hard drives. So the reason that we chose these devices specifically is because in the past we've researched fire damage to things like mobile devices, but we haven't explored damage to actual hard drives.
So, Burke, are we ready?
Let's orient the devices, seal them up, and we will start fuel loading.
Let's do it. Let's get them loaded up and outside then.
In a normal house, we would have very limited smoke coming out. This white wispy smoke that would look a lot like a dryer vent. As we see, the smoke is going to start darkening up here in a minute. Okay, we're going to start the timer now.
The heat release rates remain constant, so the burn temperatures will be the same as full scale. The fire will progress faster from the incipient phase to the fully involved phase because there are limited passive fire control measures in these structures, such as drywall and compartmentalization. The roof vent will be opened in structure fires. At some point in time, most fires will self-vent. Either a window will break or it will burn through the roof.
We can feel the temperature difference now. 8:30, so at this point in time, we're just now starting to get the first firefighters on scene. If you remember, we had that 15 seconds for call time, 64 seconds for the 911 dispatcher to dispatch the call, 80 seconds for a turnout time for the fire department to get rolling. First due units are then 4 minutes later, so we're in between first and second due units coming. There's a lot more fuel in this smoke now. You see where I lit the smoke on fire? So this is a deteriorating situation right now. Okay, so at this point in time, we're going to have a steam conversion. That's all the water we've put in there. To remember that water expands 1,600 times when it goes from water to steam. So at this point, we would consider the fire to be out. It's still smoldering, we'd be overhauling.
So now that the simulation of the structure fires is complete, the evidence has been harvested from those fires, and you can see it before you here. This is very typical of what devices look like when they come into the lab. They look very badly damaged, almost to the point of where one would believe that you couldn't get any evidence off of it. Oftentimes what we see when it gets to the lab is these devices have now been exposed to heat, fire, and water, and they were just left out to dry. But we're going to try to prove is that by actually submerging them in liquid to transport them to the lab, it will greatly increase the success rate that we have when it comes to data recovery on these devices.
I hope you liked seeing that. We absolutely love doing that. I think the favorite days at VTO are when we do field research out in the field. Let's talk about the damage that we see caused by fire. And an important note about that last video, the reason that we've been trying to figure out how to increase our efficiency lately, we have a very large federal agency in the US that has been using us as an escalation laboratory. So they'll pull devices out of a fire. They will try to work it at the local level. If they can't get the data off there, they'll send it to a regional lab. The regional lab will send it to a national level lab. At that point, it will often go to an external vendor. And VTO is kind of the last step. Everybody else has given up on it. They've said, there's just nothing else we can do. Send it to VTO. I don't know what else to do. So we get the worst of the worst after everybody else has already messed it up sometimes. And so that's why we want to figure out how we can be better and push the science forward on those hardest problems where everybody else has given up on it. The kind of damage that we see on fire really falls into 4 categories. Heat damage, which is expected because you have fire. The water and moisture damage, and this is an interesting one because when we think of putting a fire out, we've all seen examples where firefighters use water, or they may use other what we've come to learn is foams and fire suppression chemicals to put that out. One of the things that was most interesting to me as we started looking in depth at fire damage devices is that oftentimes a device may be in a different part of the structure where the fire was, and you can have massive amounts of steam that the device can be exposed to. So the device may have not even been in the line of water, or it may not have been submerged in water, but it was exposed to such radical amounts of steam that once you open that device up, you literally can pour the water out of the case, or you open the hard drive and inside the hard drive enclosure, there's water sloshing around for a device that was never directly exposed to water. And that's why we call it out as moisture damage, because liquid, whether it's in an aqueous form that moves or whether it's in a gaseous form, it still can cause damage to a circuit board. It still can be absorbed by the circuit board. It can cause short circuits, corrosion. So we can't exclude a device that's been in a fire thinking it didn't get wet. It likely still got wet because of the water exchange of water converting to steam and then proliferating out through that structure. Impact damage is another thing we frequently see. When things burn and walls start to fall, things fall down. They may have things fall on top of them. And lastly, we quite frequently see human error damage. And what I mean by this is in the attempt to try to determine, can I get data off this device? If you have people that aren't trained and don't have the right tools to deal with this, they can actually introduce additional damage. And I'll show you some examples of that as we're going through. Heat damage can be in a number of different ways. The heat can compromise the integrity of the metal. Those of you that are on the webinar today that work in fire science, you know better than us techies do that there's a robust field of literature looking at how heat can cause metal in buildings to bend and sway. And one of the things that was most interesting to me is we've never taken all of that really fascinating research from fire science and said, we know metal bends, we know it expands and contracts when it's exposed to heat. It happens on hard drives too. And why we haven't thought of that and drilled down on that topic area is really interesting to me. But we can see the compromise of the metal. The picture that you see on the top there, you see the rainbowing that's happening along that top right edge. That's actually where the platter is warped on that particular hard drive. Number two, heat can melt the plastic inside the hard drive enclosure. On our second image down, if you see the yellow or orange bit that's on that photo, that's actually a plastic head keeper. And so as that head moves across the platter and comes back into its resting position, that plastic head keeper keeps it in place and aligned. And on this particular drive, that the device got so hot that the plastic head keeper melted to the platter of this particular device. So we actually had to remove that head keeper safely from the platter to be able to address this device. Heat can melt the solder on the circuit board in between the electrical connections. And if you were here for the pre-video before the webinar started, you saw there where we mentioned that solder, that it's the metal that holds items together on a circuit board. It melts at a defined temperature. We know what temperature solder melts at, and the highest temperature we would frequently see is 230 degrees Celsius. So if a device has been in a fire higher than 230 degrees Celsius, it's very understandable that we could see solder melt on these devices. Water and moisture damage. Moisture can cause an electrical short on the circuit board or inside the hard drive enclosure. And this is one of the things that we frequently see is that agencies they'll get a hard drive and they'll go, it really doesn't look too bad. I'm just going to plug it in and see, will it turn on? In that situation, if we're not aware of the device may have absorbed water, or there may be water inside that chassis, water has the ability to conduct an electrical current. This is why you don't get in a swimming pool or a lake when there's lightning out, because you know that electricity can travel through water. That same principle applies on electronics as well. And if you have liquid there, we have to dry it completely so that we don't introduce the ability for electric current to move in erratic ways on a device or inside of a device. Moisture can cause rust and oxidation if it's not handled properly. There's ways to mitigate this rust and oxidation from happening, but specific steps need to be taken. And then lastly, moisture deposits particulate and sediments in sensitive locations. So inside of a device, you may have particulate, dirt, dust, residue left over from manufacturing that may be in this device. I'm introducing liquids into this that may have minerals and deposits inside of them. And if I let that dry and let the sediment, the particulate dry to the surface of the electronics, it becomes much more difficult to safely remove that particulate without damaging the device. Impact damage. On this top right example, you can see pitting or scratching marks on the platter, and this is indicative of a device that has been jarred. When the head is over the platter, if that head drops onto that platter, you can see that curve mark that's on the platter there, and has the potential to cause damage in that particular location. And second, any abrupt impact can cause the head assembly to move across the platters. This is why when all of us have experienced this before, back when we had drives with spinning disks in them, and we would drop our laptop and then it's clicking or it's not working, and I need to go have it fixed. That's that very sensitive mechanical movement that's happening inside this drive, jarring inside of that drive onto sensitive locations and preventing it from happening. So you think of these poor hard drives. They've just been through a fire. They've been submerged with all sorts of liquid that they were never supposed to, and now they drop and fall onto a concrete or have things fall on them. It's a wonder these things work. But that's why we're here today, is that you still can get data off these devices that have been exposed to all of these. Lastly, there's potential for damage to the circuit board or chips. This doesn't preclude us from getting data off the devices, because we know how to deal with chips and we know how to deal with circuit boards. And it could be a circuit board swap with moving the right firmware onto the chips. It could be changing the chip out and putting the right firmware onto a device that has been damaged, but that doesn't preclude us from getting the data. Human error damage. There really falls into several different things we've seen for devices that have come to us. The very first one, device attempt to power on before it's clean and dry. If you have a hard drive that's been exposed to liquid and you have not dried it out, don't plug it in to turn it on, because if you do that, you're risking damage to the circuit board, where an electrical short can happen. But also inside the chassis, you have electrical connections inside of the hard drive chassis. You have an electric motor at the bottom of this. And if there's water sitting inside there, you can cause a short circuit that will prevent the device from functioning correctly. The second thing we've seen is device opened without appropriate tools or environment. The photo you see there on the left, we were so frustrated with this one. This was a case we were working for a client that really needed the data off for their case. And it had been to all of these different labs before it came to VTO. And you can see there in the course of opening this drive, they were trying to pry the top of the hard drive off, and they had a tool that scraped across the top of the platter. And that was enough to cause this particular platter to be damaged to the point that you can't get the data off. That's a perfect example of someone who doesn't know what they're doing. They don't have the right tools. They don't have the right environment to be working on. Can make the difference. Everything about this drive that had been through a really bad fire, we could have managed. But the human error that was caused by this tool scraping across the top of it is something that we could not address. The third, a device that's disassembled without understanding the hard drive architecture and assembly. We receive drives in where they've opened it up, they've taken all the different pieces out, they've tried to put them back in. Sometimes they put the platters in out of order. Sometimes they put the platters in out of alignment. And a device that would have been a very simple recovery if somebody had just left it alone or had the right training or tools turns into a very expensive proposition to get the data, if it's even still possible. And then lastly, the poor evidence handling and shipping processes. If you see on the bottom right corner, this is a burned DVR we got. And they took this burned DVR and they put it in a trash bag. They then put the trash bag inside of a cardboard box with no packing materials. This was related to a national level case that shipped to us at VTO to look at it. The damage inside was so bad, the hard drive was moving inside this chassis. The chassis was moving inside this box with no packing materials. The damage that's caused here in this situation is just negligence. If you need to move this, move it from one of your labs to a different lab. If you need to move it to an outside vendor, pack it appropriately. Pack it as if it's something you care about, that you want to get to the other location safely, so you're not causing more damage when it's en route to the other location. I want to review with you a set of cases that we've done by a large client. This is, I reviewed this with them just a couple of weeks ago to share with them kind of the results that we were seeing on their devices. Remember, these are escalation lab cases, so this has been to everybody else. Most of the cases we're talking about here have already been to 5 different labs before it gets to VTO. For this particular client, we had worked 7 cases to date, 9 total hard drives across the 7 cases. And you can see it's about a 33% success rate of those 9 drives. And we can see that the failure falls into one of a couple of categories, either failure from heat damage or failure from human error. If we dig into that just a bit further, we can see particular cases, and all of these have been obfuscated, so that's not the original case number, but just to give you information. 3 of the failures were heat, and we know it was heat because we saw the discoloration on the platter of the metal, and we could see that the platter had actually been bent. In that situation, with all of the best research in the world, that we know of no method to address retrieving data from a platter that's actually bent from heat. We'd love to investigate that further, but it's not an area of research that's been done at this point that we can identify. We saw 3 different drives of these 9 that the failure was human error. Platters had been taken out of alignment, and there was no documentation of what that alignment was originally or supposed to be. Tool marks across the platter, like I showed you on a screen. Platters not in the correct order. And also on that last one, the last yellow one, corrosion on the platter. That's something that could be addressed with proper cleaning and proper handling if they knew what they were doing. 3 successes of these particular 9 that we were able to retrieve from devices that had been to all of these different laboratories. My motivation in sharing that with them was to help them understand that if we could reduce the human error of these drive failures, we could have raised the success rate up to 66% for these extreme catastrophic drives. And when I say extreme catastrophic drives, it is devices that have been through multi-alarm fires, complete building losses. They have been to multiple other laboratories where there was not any way to get that data off. And we still think there's a possibility of raising that rate to over 66% when you exclude those ones that is just true fire damage. You truly are at the point of catastrophic damage on those devices. Let me show you a video that we worked just a couple of years ago for a U.S. military organization, the Air Force Office of Special Investigations. This shows you something that's not a hard drive that we had some success on.
This is a cold case from 2012. There's no other evidence related to this case, so this is a last-ditch effort to see if there's anything that can be gleaned from the evidence or from the data that might still be intact inside this phone.
So we are at the VTO Lab. I'm with the Air Force Office of Special Investigations. We're working on a cold case. We had a phone that was found in a suspected homicide case. We don't know whose phone it was. The phone, we didn't even really know if it was a phone. It was kind of a melted mess of carpet and plastic and a bunch of other gunk from a fire. We put sterile suits on, gloves to try to prevent any cross-contamination. So I don't want to mess up anything that you got. Because if you're able to pull data, that's going to be probably as important as anything I can do.
Okay.
And we just found VTO. We've worked with them in the past. So we were hoping that with their expertise in recovering damaged phones, especially from fires, maybe we could get some data.
Can you give me a bag?
Like another bag just for large phone components.
Right here.
This phone is wrapped in this carpet. There might be some physical evidence.
You said one on the ear box, and then we're gonna do a second one down here on the.
Yep.
I'm gonna do ear first.
We were hoping that if we were able to, one, identify it was a phone, two, that cut it open to where we could actually get maybe some unburned pieces of it, that maybe there would be some fibers, some hair, potential DNA, potential fingerprints. We looked at it with alternate light sources to see if we could see any fibers. We saw some. We then were able to get into the phone a little bit.
After they've had a chance to pull all the other kinds of forensic evidence off, we'll continue to disassemble the phone to get to the circuit board. At that point, we will remove the chip from the board and we will retrieve the data off of the chip. We've already looked at the phone in the x-ray before we started, and the chip looks very good, looks intact. Solder connections still look good. So we're very confident at this point we'll be able to get a good acquisition of the data off of the chip. So they're trying to peel off these layers to get into the device, to get to the circuit board is the priority now. Oh yeah. Oh yeah.
Good.
Got the battery
Got a
out.
battery.
Oh man.
So it looks like it started to get, it almost looks like it's oozed a little bit. So that's where I'm saying that scalpel along that edge.
It's loose.
Is it? Okay. This is the flash chip where the data is stored. H alpha, Charlie alpha.
H alpha, Charlie alpha.
We can identify the manufacturer, the model of the chip. We can understand how much the capacity of the storage, so how much space it has on inside of it. It also will inform which adapter we put it in to read the data out of. So the SIM card out of this burned phone, we were able to extract that out. It was melted, it was swollen, and despite the fact it was melted and swollen to the melted phone, we were able to pull that out. We were able to read the data off of it. The phone number, the call history record, text messages, everything from a phone from 2012 that was severely burned.
This is data off of the SIM card. The message, the party that was involved with the message.
We were able to get data from the SIM card that was on this phone, even though it was burned, swollen, damaged, and in there. And we were able to get last text messages. So there's probably about, I don't know, 30, 40 text messages on there, including the day of his death. So we have a couple text messages and some interesting information that, so there'll be even more on the chip. So this is just kind of the external SIM card. So pretty exciting that this is burned and survived and able to get data off. So it's a credit to VTO and their skill and their expertise.
I love to see the videos. I think it helps tell the story. That way you just don't have to see my face in slides the whole time too. What is our process? What do we do here at VTO Labs? The thing that is really interesting is that a lot of the success that we see on damaged devices happens from the scene up to the point that you're doing data recovery. And you can see in this example, all of these must be done before the very first attempt to recover data. And the problem that we see is that oftentimes people will try, not just on fire damage, they'll get something that was wet, a mobile phone, they'll dry it off, and I'm going to just go ahead and try to charge it. They'll see things that may have been run over or had significant impact damage. And they'll just, let me just try to power it on and see. And at VTO, the reason we have such tremendous success on damaged devices is that's a no-go for us. We do not attempt that until all of these steps have been done. Safe collection and transport from the scene. Once we get this device, we inspect it. We are looking over everything about it. Identification, what is the device? What are the components of the device? What are the chips that are here in case we need to attack it that way? How do we clean it? I'm going to share with you how we clean things. How do we dry it? How do we repair it? All before we do the first ever attempt of data recovery. And when people turn to us and say, why do you have success pulling data off of phones that have been underwater 6 years? It's because those first 6 steps are what's critical before you ever attempt data recovery. And these are the things that we're so focused in digital forensics on how to get the data and how to analyze the data, we miss these important steps before. I've got another video for you where Matt's going to walk you through the devices that you saw burned in a previous video. He's going to bring those to the lab and walk you through that process, and then I'm going to tell you some more about it. Great questions that you have in the comments. Please keep them coming. And Matt, thank you for helping answer those as we're going through. Let's talk about some best practices for data recovery. The number one best practice that we recommend for any device that's been burned or any device that's been damaged, that you don't know the level of damage and what's been done, do not power on a burned device or attempt to recover data until the level of damage has been assessed. This we feel like is one of the very most fundamental critical steps. And we hear agencies around the world that say, I've got it, I'm just going to try it. It doesn't look too bad. They plug that hard drive in. And the reason people do this is that they have some measure of success sometimes. And then what's hard to quantify is the ones that you don't have success on. Is it the damage from the fire or the water or the other damage that it was exposed to? Or is it damage because you just introduced an electrical current into a device that the circuit board has been disrupted? There's liquid inside, there's a humid environment that's caused a short circuit. You don't know. And that's why until you can assess the level of damage, you should not power a device on. The other thing that's really hard, and this is probably the thing that has been the biggest obstacle for us to overcome in people's understanding, is that wet devices need to stay wet. And that we almost every week I'll have an agency call from somewhere in the world and say, we just got a device out of a lake, an ocean, the water, a river. What do we do? How do we dry it? And I say, whoop. Stop right where you are. Don't dry it on the crime scene. It needs to stay wet. And the reason is that water, liquid, steam, any sort of liquid that's been introduced to a device allows particulates and minerals to move inside of that device. It may introduce a particulate into that device. And if you allow it to dry before it's cleaned, you're going to increase the level of damage on that device. Devices that have been dried improperly, you can see on the printed circuit boards, the actual PCB traces lifting off of the board or completely corroded, where you'll need to repair the circuit board. On hard drives, we find that the calcification, the mineral deposits, the sediment that's in the water, the sediment that may be in the drive from filters on the drive or residual manufacturing material will adhere to the surface of the platters and oftentimes make it incredibly difficult to clean off without damaging it. And in some instances, though, that complication can be catastrophic. And people say, but water, don't put water on electronics. Every electronic you've ever touched, a phone, a computer, a server, a hard drive, as part of the manufacturing process, the very last step that's done on circuit boards at the end of a manufacturing process is they clean them in this large industrial sized dishwasher. They actually wash the manufacturing residue and flux off of these devices and then dry it. And if you don't believe me, I would encourage you to go look up IPC JDEC standards for manufacturing of electronic assemblies. But before I came to VTO Labs, my background is the electronics manufacturing industry. I was in that for almost 17 years in electronics manufacturing before I started VTO. And that's where I know what's done to these devices in the manufacturing environment. I know they've already been wet. And if we can control the moisture, the drying temperature, the cleaning process, we can increase our efficiency significantly. That's why we have such high success rate on getting data out of devices that have been wet, because we know wet devices need to stay wet until you can clean them properly and dry them properly. And then you can power them on or remove the chip and put it on a different donor device, read the chip directly, or have it cleaned and dried sufficient to pull the data from the hard drive. Best practices, do it right the first time. Following a defined methodology for data recovery is less expensive, more successful, and faster than making mistakes on evidence devices. If you have, if you ever hear me speak anywhere in the world, one of the things that you'll often hear me say in conferences is don't practice on evidence devices. And agencies from very small agencies in areas around the world to the largest law enforcement agencies in the world will make mistakes when they practice something on a piece of evidence. And you can think, wow, does that ever really happen? It happens every day somewhere in the world where somebody gets a new device, they're not quite sure what to do, they don't have another example of that device, they've never seen damage like this before, and I'll just try it. I'll just plug it in and see what I can do. I'll try to figure it out on this one because I don't have another example. Don't practice on evidence. Don't practice on evidence. Don't practice on evidence. By following a methodology and training your lab to follow the same processes each time, you can increase your success rate. You can mitigate the additional damage that you may be doing to devices, and you can have more success in getting data off of those devices. Best practices. Rice is not the best way to dry devices. I hear this so much. It is an urban legend that's out on the internet that if I get a wet device, I'll put it in rice and that'll dry it. We actually tested in a laboratory all of the different methods that you can use to dry a device. Vacuum oven, convection oven, we used a home toaster oven, desiccants, rice, air dry. I'm forgetting one right now off the top of my head. And we measured what is the efficacy of drying all of these devices. The thing that our research showed in this problem set, using defined scientific studies of how to measure moisture absorption and the removal of absorption, is that rice is equivalent to air dry. If you're going to put it in rice, you may as well just lay it on a lab bench and let it dry, because it will dry at the same rate of removing that moisture out of the device. The way we dry things, and you may have seen it in our lab, we have a convection oven that we have used to dry hundreds, maybe thousands of devices at this point, to remove all of the liquid from the circuit board, from the enclosure, from the chips. And you say, but how do do I just turn it on? We used the temperatures defined in the IPC JDEC standards for manufacturers that have wet devices. So we just follow the standards that are already out there, already published. And this goes back to something you heard me say earlier, is that our research must be multidisciplinary. As a techie, I don't need to go figure out how to dry devices. Somebody else has already done this, that has spent their entire career learning how to do this. So we follow their methods, their temperatures, their durations, and it causes increased success in what we do. Best practices: package evidence safely for transport. If you need to move it from one location to another, make sure that you're not inflicting additional damage on that evidence by moving it. Put it in make sure it's safe in the enclosure. Make sure that you have an enclosure that you can safely seal, so that as you move that to another location, the lab technician that gets it and opens it up is going to say, I have a device here that's as close to possible as it was on the scene. No additional damage has been introduced as part of this process. What about other electronic devices? Those of you that are here on the webinar today, I want to introduce to you that you may have other kinds of devices on fire scenes that you've not been thinking about. And we all know that there's computers, there's mobile phones, there's tablets. But what about some of the other kinds of devices we find in existing residential and commercial infrastructure? It may be Internet of Things devices. So it could be cameras that are there that are Internet of Things cameras. It could be sensors that are there. All of those things may have data that could help you on your fire investigation. And you should not think that just because it's been burned, you can't get the data off. The data very likely still may be there. Thermostats, DVRs is something that we do quite a bit of. Building control systems. As we see more devices inside a structure being connected, we could understand that there may be lots of electronic devices in that building that are telling the story, that are telling when the alarm happened, what were the temperatures in that space, does it measure the oxygen levels? Those are things that you may think are damaged. We may just be leaving them on the fire scene right now. They may have data that can be useful for you. Alarm systems as well. The last thing that I wanted to mention to you is that if we have been working quite a bit on figuring out how to decontaminate devices that are biohazardous to us. If they've been exposed to bloodborne pathogens, if they've been exposed to dangerous chemicals, if they've been exposed to, this example is supposed to replicate a meth laboratory. If they've been exposed to drug residues or a meth laboratory environment, how can we clean those to make them safe for digital forensics examiners? If you go to our website, you can find out more information about that. We actually just did a webinar last week on decontaminating biohazardous devices. And you can clean devices that have been exposed to hepatitis and Ebola and fentanyl in such a way that the device is safe to handle for your digital forensics examiners to still be able to get that data off. Just because it's been exposed to a hazardous condition doesn't mean that it can't be cleaned in such a way that the data can still be retrieved. So please reach out if you need some more information about that. We would love to partner with you. If you have a specific challenge we haven't mentioned in digital evidence, and it may be a new device, it may be a new problem set we've not heard about. This is what we do really well at VTO Labs, is work with people just like yourself to find answers to some of these complicated problems. If fire is an area that you deal in fire investigations, we've identified from some very specific research questions that should be explored further, and we're looking for agencies to collaborate with. So if you are in an agency that is dealing with fire damage kinds of devices, we've got more questions. We've got other things that should be investigated, and we'd love to partner with you to do that. I'll pause for just a moment. Matt, do we have any other questions in the comments? I'm just looking at all the activity that's been happening on the side there. I'm going to drop my email address in the comments there. And if we can ever be of assistance, please don't hesitate to reach out. We're here to support you wherever you are in the world, whatever challenges you're facing in digital forensics. We're here to help you to figure out how to get this data to win the cases that you need to. So thank you for your time. I hope you learned something today, and we appreciate you coming to the webinar. Thank you.